Welcome to today's Explainer. We are taking a fascinating micro to macro journey straight into the D-block elements to see exactly how tiny atomic quarks literally build our world. I am incredibly excited to guide you through this because this specific group of elements, they truly represent the bridge between fundamental invisible chemistry and the real-world applications we rely on every single day.
Here is our roadmap for today's Explainer. We'll start with 1. Meet the transition metals, move on to 2. The d-orbital secret sauce, then hit 3. Superpowers, color and magnetism, 4. Catalysts and compounds, and finally, 5. Industry and biology applications.
All right, let's dive right into Section 1. Meet the transition metals, bridging the periodic table.
To really grasp the importance of what we're looking at today, we have to start by asking a simple question. Have you ever actually stopped to wonder what makes rust red? Or why gemstones are so vibrant? Or what makes steel virtually indestructible? On the surface, these seem like totally wildly different macroscopic properties, right? But they all trace back to the exact same microscopic family occupying the middle portion of the periodic table, the transition elements.
So, the crucial point here lies in the official IUPAC definition. A transition element isn't just any random metal shoved in the middle of the table. To be in the club, it absolutely must have an incomplete D subshell in its atom, or in one of its oxidation states. That incomplete D subshell is the real secret behind their unique behaviors. It means they have chemical room to maneuver. And this causes a fascinating transition in properties between the highly reactive S-block metals on the far left side of the table and the much less reactive key-block elements on the right.
These elements occupy groups 3 to 12, and they're divided into 4 distinct series. But I want you to pay special attention to the first transition series, which fills the 3D orbital and spans from scandium to zinc. Because of their immense industrial applications and huge biological significance, this specific row of elements is arguably the most important series in all of chemistry. Truly understanding this one row unlocks the secrets of so much of our modern world.
Moving right along to Section 2. The d-orbital secret sauce, breaking the atomic rules.
To really understand transition metals, we have to look at how their electrons are organized. This formula establishes the baseline rules. The general electronic configuration is n-1d 1 to 10, ns 1 to 2. Okay, in simple terms, this means the last electron doesn't go into the outermost shell like you might logically expect. Instead, it enters the d orbital of the penultimate, or second-to-last shell. It's kind of like packing a car for a road trip and deciding to put that final heavy bag in the back seat rather than the trunk. This close packing of inner d and outer s electrons creates intense metallic bonds, and that is exactly what makes these metals so exceptionally hard, lustrous, and dense. But here is where things get really interesting. Elements like chromium and copper, they completely break the expected rules to achieve extra stability. Logically, we'd expect chromium to end in 3d4 4s2, but instead, it spontaneously shifts an electron to become 3d5 4s1. Why? Because a half-filled d orbital with 5 electrons is incredibly stable. It balances the atomic energies perfectly. And copper does the exact same trick. It steals an s electron to create a fully filled 3d10 orbital. They essentially prioritize maximum internal stability over the standard filling order. Pretty smart, right? Now, this brings us to a super fascinating piece of chemical trivia. Even though zinc sits at the very end of that highly important first transition series we just talked about, it is frequently excluded from the true transition metal club in a lot of scientific syllabi. So, why would it be kicked out of its own neighborhood? Well, the answer is hidden right there in the orbitals. Zinc has a completely filled d orbital. Its configuration ends in 3d10 4s2. And get this, even when it becomes an ion and loses 2 outermost electrons to bond with other elements, its inner d orbital remains totally full. Remember our IUPAC definition from earlier? A transition metal needs an incomplete d subshell? Because zinc is locked completely full, it fundamentally lacks so many of the hallmark transition properties we are about to dive into.
Let's move to Section 3, Superpowers, Color and Magnetism, Seeing the Invisible Micro-World.
Just look at this massive number. +7? This represents the maximum oxidation state of manganese. Because both the outermost s electrons and the inner d electrons can participate in chemical bonding, transition elements show highly variable oxidation states. So, while iron might comfortably sit at a +2 or +3 charge, manganese can use all of its outer and inner available electrons to reach an absolutely incredible +7 state. This showcases the totally unmatched chemical flexibility of the d block. And you know what?
That exact same atomic flexibility allows for something called d-d electronic transitions. This is the precise microscopic mechanism that gives these compounds their brilliant colors. When white light hits a transition metal ion, that energy causes electrons to literally jump between split, partially filled d-orbitals. You see, the atom absorbs very specific wavelengths of that white light to fuel the electron's jump. Whatever wavelengths are left over, the ones that weren't absorbed, get reflected back to our eyes as a specific, vivid color. It is literally quantum mechanics creating everyday beauty. The contrast is striking when we compare them. If an ion has completely empty d-orbitals, like scandium 3+, or completely full ones, like our buddy's zinc 2+, there is simply no room for electrons to jump. And no jump means no light is absorbed, resulting in a colorless or white compound. But with partially filled orbitals, like copper 2+, the electrons can jump freely back and forth, absorbing specific light and reflecting back that rich, characteristic blue we instantly associate with copper compounds.
But wait, those exact same unpaired jumping electrons are actually doing double duty. They don't just create color. They act like literal tiny individual magnets. When a transition metal has unpaired electrons, their spin generates a strong magnetic force known as paramagnetism. The more unpaired electrons a metal has, like iron with its 5 unpaired 3d electrons, the stronger the overall magnetic pull. And this is exactly why iron is the absolute king of magnetism in our daily lives.
All right, Section 4, Catalysts and Compounds, the building blocks of chemistry.
Because they can so easily shuffle electrons around by changing those oxidation states we talked about earlier, transition metals are some of the best catalysts in the world. This step-by-step breakdown of the Haber process shows exactly how crucial they are. By introducing nitrogen and hydrogen gas over an iron catalyst, we can efficiently synthesize ammonia for fertilizers. The iron surface physically absorbs the gases, using its variable oxidation states to lend and borrow electrons, which temporarily lowers the reaction's energy barrier. This dramatically speeds up ammonia production, a process that is absolutely vital for sustaining modern global agriculture.
But they don't just speed up reactions. They physically build our world. Because of how their crystal lattices are structured, transition metals actually have tiny gaps between their atoms. Small atoms like hydrogen, carbon, or nitrogen can get trapped right in these gaps, acting almost like hard mortar between bricks. This creates what are called interstitial compounds, like titanium carbide, which are incredibly tough and have massive melting points, because the metal layers can no longer easily slide past one another. Furthermore, because transition metals in a series have very similar atomic sizes, they can easily mix with each other to form alloys. Mix iron and carbon, and you get steel. Mix copper and zinc, and you get brass.
Finally, let's hit Section 5, Industry and Biology Applications, the macro world.
It is just wild to realize that life on Earth is fundamentally dependent on these metals. The iron holding oxygen in your blood's hemoglobin, the cobalt nestled right at the core of vitamin B12, the manganese driving photosynthesis in every green plant on the planet. Biological systems have evolved over billions of years to perfectly harness the unique coordination chemistry and electron shuffling abilities of the transition elements. Without them, biological energy transfer would completely grind to a halt.
And of course, beyond biology, these metals are the literal backbone of modern engineering and industry. We extract iron from hematite in massive blast furnaces to build our cities. We use the corrosion-resistant properties of chromium and nickel to plate our appliances. We string excellent conductors like copper across the globe to power our electrical grids. And we utilize lightweight, incredibly strong titanium for everything from aerospace engineering to life-saving medical implants.
To wrap up our explainer today, I want to leave you with this final thought. It is so easy to take our macroscopic reality for granted. But the strength of a steel bridge, the color of a ruby, and the oxygen coursing through your pulse right now are all dictated by the microscopic, rule-breaking quirks of incomplete d-orbitals. So the next time you look at the world around you, ask yourself, what other invisible atomic secrets are quietly holding our universe together? Thank you so much for exploring the transition elements with me, and keep questioning the science behind your world.